Ever wonder how AI systems like GPT or AlphaFold achieve such mind-bending complexity? Today, we're diving deep into the architecture of modern neural networks, exploring how layers, activation functions, and optimization techniques work together to mimic human-like pattern recognition. This isn't just theory. It's the backbone of every recommendation engine, language model, and autonomous system you interact with today. Let's break it down. At their core, neural networks are mathematical structures inspired by biological neurons. Imagine a multi-layered pipeline. Input layers receive raw data, hidden layers process it through weighted connections, and output layers produce predictions. Each connection has a weight, a numerical value that determines the signal's strength. During training, these weights are adjusted to minimize error, a process called backpropagation. But here's the kicker. The magic happens in the activation functions. Functions like ReLU or sigmoid introduce nonlinearity, allowing the network to model complex relationships. Without them, a neural network would just be a linear regression model, useless for tasks like image recognition or natural language processing. Let's talk numbers. When a model makes a prediction, it compares it to the true label using a loss function. Common choices include mean-squared error for regression or cross-entropy for classification. The goal? Minimize this loss. But how? Enter optimization algorithms like stochastic gradient descent, SGD, or its modern variants, Adam and RMSProp. These algorithms tweak weights iteratively, following the gradient of the loss function. Think of it as a hiker descending a mountain. Each step is informed by the slope of the terrain. But here's where it gets tricky. Vanishing gradients in deep networks can stall training. That's why techniques like batch normalization and residual connections became game changers, enabling the training of networks with dozens of layers. Now let's escalate. Convolutional neural networks, CNNs, revolutionized computer vision by leveraging filters to detect spatial hierarchies, edges, textures, objects. Recurrent neural networks, RNNs, and their LSTM-GRU variants handled sequential data, powering everything from speech recognition to machine translation. But the real leap came with transformers. By replacing recurrent layers with self-attention mechanisms, transformers decode relationships between all elements in a sequence simultaneously. This allowed models like BERT and GPT to process context at unprecedented scales. The key innovation: the attention matrix, which assigns weights to every pair of tokens, enabling the model to focus on relevant parts of the input. It's like giving the network a spotlight to highlight what matters most. Beyond the math, these architectures have tangible impacts. A CNN can diagnose skin cancer from images with dermatologist-level accuracy. Transformers power real-time language translation and code generation. But with power comes responsibility. Overfitting, data bias, and energy consumption are critical challenges. Techniques like dropout regularization, data augmentation, and efficient architectures, e.g., MobileNet, address some issues, while ethical frameworks strive to ensure fairness and transparency. The future isn't just about building smarter models, it's about building smarter, more equitable systems. Neural networks aren't just lines of code, they're a testament to humanity's quest to decode complexity. From perceptrons to transformers, each innovation has pushed the boundaries of what's possible. As researchers continue to refine architectures, optimize training, and tackle ethical dilemmas, the next breakthrough could be just around the corner. If you're passionate about AI, now is the time to dive in, because the future isn't just being built, it's being learned. Thanks for watching. If you want to explore the math behind backpropagation or experiment with transformer architectures, check the description for links to research papers and coding tutorials. Hit subscribe for more deep dives into AI's most fascinating concepts. Until next time, keep learning.